Hi all, my name is Serhii and I would like to present to you the results of our paper application for vision transformers and 3D convolutional neural networks for sign language cluster recognition. Sign language is an essential mode of communication for deaf and hard of hearing individuals. Sign language recognition, or SLR, is a challenging task as sign languages are highly complex with a wide of range of variations and nuances. One of the primary challenges in SLR is the complexity of sign languages. There are over 300 sign languages used worldwide, each with its own grammar, vocabulary, and dialects. Furthermore, sign languages are highly context dependent, with the meaning of signs often varying depending on the speaker's location, age, gender, and culture. Another challenge in SLR is the variability in sign styles. Signers may use different hand shapes, positions, and movements to convey the same message. Moreover, the speed and duration of signs can vary, adding further complexity to the task. Thus, SLR systems must be robust to variations in sign styles as well as to variations in lighting conditions and camera angles. One of the main challenges in sign language recognition also is collecting and annotating large datasets of sign language gestures, which are required to train and evaluate machine learning models. This can be particularly difficult for sign languages that are not widely spoken or documented. The limitation of SLR is the lack of large-scale annotated datasets. While there are several datasets available for SLR, they are relatively small, limiting the performance of machine learning algorithms. Whatever. Another issue in SLR is the lack of real-time performance. SLR systems often require high computational resources, making it challenging to achieve real-time performance on mobile devices or in low resource settings. So, the sign language recognition is a challenge task that requires robust and accurate recognition of complex hand gestures, facial expressions, and body movements. While several solutions have been proposed to address the limitations and challenges of SLR, there are still several unsolved issues such as real-time performance, variability in sign styles, the lack of large-scale annotated datasets. Overall, sign language recognition is still an important problem with a potential application in fields such as assistive technologies, education, and communication for the deaf and hard of hearing individuals. So there are various methods for sign language recognition that have been proposed and tested over the years. Here are some of the most widespread methods for such systems. So the first one is template matching. Is a simple and intuitive approach where the hand movements of the signers are matched against a predefined set of templates to recognize the sign. The template matching method involves capturing a series of hand poses and storing them as templates. During the recognition, the input sequence is compared to each template and the sign is identified based on the closest match. The hidden Markov models are also probabilistic models used in speech recognition as a tool that can model the temporal dependencies in sign language by capturing the transitions between the hand shapes and movements. Support vector machines, as a type of machine learning algorithm, can classify sign language sequences by finding their hyperplanes that separate the data points into their respective classes. So another approach is to use 3D depth sensors, such as Microsoft Kinect. It can give the possibility to capture the 3D shape and positions of the signer's hands. And of course, the deep learning methods such as convolutional neural networks and recurrent neural networks have been used in SLR and have shown significant improvements in the performance. CNNs can learn the special features of sign language sequences, while RNNs can capture the temporal dependencies between hand movements. Several approaches to deep learning could be defined for the relevant task and could be quite efficient in the real application. The first one is post-TCN, that is the deep learning model that uses the temporal convolutional networks, TCNs, to capture the temporal dependencies in sign language gestures. Post-TGCNN is a deep learning model that uses the graph convolutional networks to capture the spatial dependencies between the joints in sign language gestures, and a temporal convolutional network, TCN, to capture the temporal dependencies. Inflated 3D ConvNet or I3D is a deep learning model that uses a 3D convolutional neural network to extract the spatial temporal features from sign language gestures. And sign language transformers is a transformer-based model that uses self-attention mechanism to learn the spatial and temporal features of sign language gestures. The model uses a pre-trained backbone network such as ResNet or FishNet to extract the visual features from the frames, which are then fed into a transformer encoder-decoder architecture. The attention mechanism in the model allows it to focus on the most relevant parts of the sequence and improve their cognition accuracy. Now, this approach is widely used in continuous sign language translations. In summary, there are various deep learning models that can be used for sign language recognition, such as post-TGCNN, I3D, post-TCNN, and SLT. These models differ in their architecture and the ability to capture spatial and temporal dependencies in sign language gestures. In Ukraine, the task of sign language recognition is really actual and important in context of war and necessity to develop the special governments to support and provide assist and inclusion in society the people who were suffered from the war and have problems with hearing. There are several works of national scientists who have investigated the problem of sign recognition and proposed special techniques and systems for communication and translating it into the sign language. Nevertheless, there are still unsolved issues and necessity of new approaches and adapting the existing methods is quite high. So the goal of our article or paper was to test mentioned above approaches and to build this simple transformer-based model for sign language recognition and compare its efficiency with the standard approach of using 3D convolutions. We want to clarify and define on the very first level without any neural network tricks or additional approaches with which approach could be more accurate for our task. For our experiment, the LSA64 dataset was used. This dataset is a dataset for Argentinian sign language, and it represents a collection of video sequences designed for the task of sign language recognition in the Argentinian sign language. For our experiments, firstly we made some labels for the dataset and then clustered them into 3 logical groups. That was done to have more labels in each of the ground truth classes. The classes are colors signs that consist of next initial classes or signs like red, green, yellow, light blue. The second class is food signs, consist of sweet milk, water, food, and the last class is verb signs, consist of the help, thanks verbs, and so on. The labels were randomly split into the trained test sets. 385 labels went to train and 165 labels to the test set. Note that for experiments, the proportion of each class was saved in both train and test sets. In this part, I will tell you in more details about the transformer-based and 3D convolution-based models that were used in our experiments. A neural network that uses 3D convolutions for video analysis typically consists of multiple layers of 3D convolutions, a convolutional, pooling, and fully connected layers. 3D convolutions are a type of convolution layers that considers the spatial and temporal dimensions of the input data. In this case of video analysis, the input is a sequence of frames, and the 3D convolution layer applies a kernel to each frame and its neighboring frames in the temporal dimension to extract features that capture both spatial and temporal information. After the 3D convolution layers, pooling layers are often used to downsample the feature maps and reduce the spatial dimensionality of the data. This helps to reduce the number of parameters in the model and prevent overfitting. Finally, fully connected layers are used to classify the input video sequence into one or more classes. These layers take the flattened feature maps from the conv layers and apply a set of ways to produce the probability distributions over the possible classes. The approach of video vision transformer or VI-VIT involves dividing the video into small spatial temporal regions of interest called tubulets and processing them using self-attention mechanisms similar to those used in the NLP models. Here, a brief overview of how the VI-VIT model is with tablet embeddings works. The first step is the tablet extractions. The first step is to extract this tablet from the input video. This can be done using a variety of techniques such as object detection, tracking, or motion analysis. Each tablet is represented as a sequence of T frames, where each frame is H on W on C tensors, representing the pixel values of the video frame. Then goes the flattening and linear projections. So each frame in the tablet is flattened into a sequence of patches, and these patches are then linearly projected into the higher dimensional embedding space of size D using the trainable linear layer. Multi-head self-attention layer, it's the projected, so the next step is that the projected sequences are then passed through the multi-head self-attention layers. Each layer computes the attention weights between all pairs of patch embeddings in the sequence, and uses these weights to compute and weighted sum of the patch embeddings. So this allows the model to attend to different regions of the tablet depending on the task at hand. After each self-attention layer, their output is passed through a feed-forward network with the RLU activation function. This network applies a linear transformation to the input, followed by a non-linear activation function. This helps the model to capture more complex relationships between the patch embeddings in the sequence. And aggregation, finally, the output of the last self-attention layer is aggregated across all frames in the tablet to obtain a single vector representation of the tablet. These vectors are then passed through the linear layer to predict the class label for the entire tablet. In our experiments, we used the vision transformer and 3D convolutions for comparison on our data, which were trained on the different batch sizes 3, 32, 128, and 385, the length of trained data. Each of the models was trained on 30 epochs with the input size of videos equals to 25, 64, 64, and 3. And during the training, the history of the accuracy were stored, so as a result, only those model weights are saved and loaded for those approaches that had the best test accuracy. That was done to prevent the possible model overfitting. In the table, it seems that the VI-VAT models with the small batch sizes have higher quality. But having in mind the train accuracy as well, we can notice that such models are more easily overfitted. That means that VI-VAT model is faster in training flow to get the high quality. The blue and orange lines on the plot represent VI-VAT models with the 3 and 32 batch sizes and have the highest metrics over all presented epochs. 3D models that are on the plot, purple and brown ones, are at the bottom in terms of quality and time training. On the other hand, the VI-VAT model for the future investigations, more approaches for fixing the model overfitting issue should be applied, for instance, augmentation, especially by working with small amount of data. Such logic could be traced on the plots below as well. Note that in figures, the loss and accuracy are normalized to be presented on the same scale, which gives the opportunity to analyze the overfitting issues there. As you could see on the first 4 plots where the VI-VAT models are represented, the accuracy is higher and more faster achievable, but the training flow has more instability. Meanwhile, the 3D models are slower but predictable, and only in the last epochs they are getting closer to the transform-based model in terms of metrics. So in this presentation, we discussed the most relevant practices and approaches for SLR. While significant progress has been made in sign language recognition using modern methods, there are still some important issues that remains unsolved. Large variability in sign language, the availability of large, diverse dataset is crucial for training and evaluation machine learning models for SLR. Sign language gestures can be occluded or noisy due to factors such as clothing, lighting, and background clutter. Sign language recognition systems are typically trained on a limited set of sign language gestures, which can impact the ability to recognize new or rare signs. The task of sign recognition in this presentation was solved for real dataset. It was shown how to implement the existing approaches on different sizes of the existing data and what to do to receive the most high accuracy. Our experiments aim to compare the performance of the vision transformer and 3D convolutional CNN models on sign language recognition. We trained both models on different batch sizes and evaluated the accuracy using the top K metric. Our analysis shows that VI-VAT models with a small batch size achieved higher quality but were more prone to overfitting. To address this issue, feature investigation should explore approaches such as data augmentation to improve the generalization of transform-based models, especially when working with the limited amounts of data. It was also shown that it's needed to search the compromise between speed, accuracy, and overfitting issue, as well as between length of the dataset. Overall, our results provide valuable insights into the strengths and limitations of different models for sign language recognition and offer a starting point for further research in this area by using vision transformers and additional approaches in conjunctions with, for example, pose estimation, hands recognition, etc., with vision transformers before classification itself. Thank you.